A star's life trajectory that spans millions and billions of years is determined by its mass or how much gas was initially collected and collapsed to form this particular star. This gas is precisely the substance which serves as stars' fuel. Stars use this mass as fuel by the virtue of a phenomena known as nuclear fusion. So, what is nuclear fusion? Whenever nuclei collide with enough energy so as to overcome the electromagnetic repulsion between them, the strong nuclear force dominates and they fuse together, releasing gigantic amounts of energy as dictated by the Einstein's famous E is equal to mc square relation. So this particular phenomena is precisely the phenomena of nuclear fusion. Stars counter the effect of gravitational collapse by releasing outward energy by fusing nuclei in their ultra-hot core. So, mass seems to be the crucial factor in our discussions till now. Hence, we shall now discuss about what happens to stars of various mass ranges. Let's start with a low mass star, that is the smallest amount of material that can sufficiently trigger nuclear fusion. This roughly is about 13 Jupiter masses. Any star formation will begin with the collapse of a cloud of gas and dust at least a few light years across. The material to collapse is commonly hydrogen and helium, as this was what remained after the short 17 minutes of the nucleosynthesis following the Big Bang. This matter contracts due to gravity until the temperature rises to a few million degrees and starting nuclear fusion, and ultimately establishing an equilibrium. Fusion reactions begin with the fusion of two protons and then subsequent beta decay to get a deuteron, which is a nucleus of heavy hydrogen. These deuterons then make helium, which has two protons and two neutrons. Such star will continue in this manner for billions of years, slowly fusing all of the hydrogen in its core into helium and maintaining a relatively steady size, temperature, and luminosity until almost all of the hydrogen is gone. After this point, things really begin to change. The core of the star will shrink and get hotter, making the remaining hydrogen burn even faster and radiating away energy, thereby pushing the outer layers away from the core. As the outer layers expand, the star will become what we call a red giant star. Stars can maintain this new status for around a billion years, but after almost all the hydrogen is gone, the core gets even smaller and becomes hot enough to fuse the helium nuclei into larger nuclei like carbon and then oxygen. Once the core is predominantly carbon and oxygen, the star has very little material left to burn. Hence, the core will collapse and the star enters the asymptotic giant branch. It will grow rapidly and become a giant star again. Finally, the last bursts of energy eject the outer layer, pushing it away from the core, leaving behind only a very hot core about the size of the Earth. Now, as it has no more fuel to burn and it is not hot enough to fuse carbon or oxygen nuclei, this will gradually cool and will contract further, finally leaving what we call a white dwarf star. This was our discussion for a low mass star. Let's now start with a high mass star. These are much more massive than our Sun. Here, more mass means more gravity, which means that the inward force is much stronger and the star gets much hotter. Hotter temperature implies faster fusion rate, which generates larger outward pressure. As the fuel starts running out, the core contracts and produces more energy. The star will then swell up into a giant star. But while the core of a high mass star continues to contract, it gets much hotter in comparison to the core of a low mass star, and it becomes possible to fuse helium nuclei to form carbon, carbon to oxygen, and then neon, and then to more heavier elements. At the center, we have the heaviest elements that can be fused within a star, that iron. This occurs in different layers, and the star is left with an inner core of stable iron nuclei, and thus further release of energy through fusion is not possible. At this stage, gravity wins the fight, and the star collapses instantaneously, and the outer layers bounces off the core and triggers an explosion which is called a supernova. In this event, all of the heavy nuclei created inside the star is thrown out in space. The gigantic burst of energy emitted in this brief moment produces elements like nickel, zinc, gold that are heavier than iron. Supernova does not leave behind a white dwarf. Only lower mass stars that begin with less than about 8 solar masses leave behind white dwarfs. White dwarfs are supported against gravitational collapse by the degeneracy pressure of electrons. But for a high mass star, when the mass of the remnant core of the star is above a certain limit, two things can happen. If the remnant core is between 1.4 and 3 solar masses, which is generated by a star that was originally about 10 to 40 solar masses, the core will not be able to support its own gravity, and it will collapse with such a tremendous force that all the electrons will be squeezed into protons and they combine to form neutrons. The object that remains is like a ball of neutrons containing the mass of the core of the star. But if the core of the star is above 3 solar masses, even the outward pressure of neutrons, which is called neutron degeneracy pressure, is not enough to stop the tremendous gravity, and the neutrons will be crushed together as the remaining mass collapses into a single point of infinite density. This object is called a black hole. Now, as we have seen, stars at the end of their life cycles turn either to a white dwarf, neutron star, or a black hole. These objects collectively are called compact objects. We shall now discuss about one of the most significant results in the field of compact stars known as Chandrasekhar limit. This result was given by the Indian astrophysicist as Chandrasekhar. When this was first suggested, the neutron star was yet to be discovered, and the possibility of stable stellar configurations at densities higher than that of white dwarfs was unknown. The existence of such a mass limit therefore sparked the thought that the ultimate fate of more massive stars might be infinitely compact configurations, which we now call black holes. This was an uncomfortable thought at that time, and the suggestion of the mass limit, correct though it was, required a long time to gain acceptance in the astronomical community. Now we shall discuss about some of the corrections made to Chandrasekhar limit in recent years. Indian Institute of Science researcher Banibrato Mukhopadhyay noted that Chandrasekhar's work did not include the effect of magnetic field in his calculations, whereas the Sloan Digital Sky Survey, which is a project launched in 2000 to map a large part of the universe, has discovered several magnetized white dwarfs with surface magnetic fields as high as 10 to the power 9 Gauss. Their aim was to obtain the maximum possible mass of such magnetized white dwarfs and hence a new Chandrasekhar limit. They showed that strongly magnetized white dwarfs exhibit a limit of 2.58 solar mass, thus significantly violating the Chandrasekhar mass limit of 1.44 solar mass. They arrived at this new mass limit by exploiting the effects of magnetic fields in compact objects. Now, who knows whether this is the final limit of white dwarf mass? We shall end this video by noting that there is still a lot to know about the field of compact stars.